Alright, so we are ready. We've got DMAPP right here, or IPP. And what we need to do in order to use these is we need to do an SN1 ionization condensation elimination reaction. And the purpose for doing that is to remove our inorganic pyrophosphate molecule. So what we're going to do is use this double bond right here on our IPP to basically form a bond with any other kind of precursor. So this is DMAPP or any other longer isoprene unit with PPI. Okay, so essentially what we've got is we've got the formation of this carbocation. This double bond right here is going to swing down there. We're going to have this carbocation present there temporarily. We'll lose this hydrogen right here, put a double bond right there, and now all of a sudden we've got two 5-carbon molecules. Well, one potentially longer than 5 carbons, but we've added our previously 5-carbon pyrophosphate molecule to another longer chain so that we can make a longer and longer isoprene unit. Now, the enzyme that catalyzes the combination of DMAPP and IPP is an enzyme known as Prenyltransferase. Okay, so what we have here is you have these commonly referred to head and tail ends of your isoprene units. This right here is the head, and this is the tail. Okay, now this is distinct because what we're talking about here is a head-to-tail combination. Prenyltransferase is an enzyme that is going to catalyze that head-to-tail reaction and liberate off those inorganic pyrophosphate molecules. These two carbons, this DMAPP and IPP, they're going to combine to make a molecule of geranyl pyrophosphate. Now this isn't necessarily the direction that we're going to go, but the kind of fun thing about this is you can add, or you can take a molecule of GPP, you can add GPP to GPP. Okay, so this is 10 carbons, this is 10 carbons. You're going to make a 20 carbon molecule. Okay, now what I would say that's kind of fun about this is that one 20 carbon molecule that results from the combination of a geranyl pyrophosphate and a geranyl pyrophosphate, that molecule is known as GGPP, geranyl pyrophosphate, because it has two geranyl groups added together and one pyrophosphate. Okay, but that's just a little aside there. Now, with respect to what prenyltransferase is also going to do, it's also capable of taking a 10 carbon geranyl pyrophosphate molecule and a 5 carbon IPP molecule and do another head-to-tail combination, or a head-to-tail reaction, in which case it makes farnesyl pyrophosphate of 15 carbons. Okay, now that 15 carbon reaction, or that 15 carbon product, is fairly significant because that 15 carbon product can be used by the enzyme the enzyme squalene synthase. Now what squalene synthase does is a head-to-head reaction. So again, head to head, two heads of our farnesyl pyrophosphate molecules, and what we can make is this molecule right here, known as squalene. Now, squalene is a major part of membranes. It is a lipid. You don't have to know the structure of this or anything like that. Just know that what you're doing is you're removing a pair of pyrophosphate molecules because this is a head-to-head reaction. So both of those pyrophosphate molecules from the heads of those farnesyl pyrophosphates will be eliminated, in which case then you couldn't really do another head-to-head reaction because of the fact that you've gotten rid of those. Now, after you form that squalene molecule, what you need to do is you need to begin moving towards cyclizing it. And so the enzyme squalene epoxidase is going to help you do that. So it's going to glue those rings together, and what it's going to require is NADPH and some oxygen. Now, once you've begun moving in that direction, and you have this epoxy ring out here in the form of, or on this 2,3-oxidosqualene molecule, well, you're going to open that ring up. Your enzyme is going to donate a proton. It's going to open that ring up, and now all of a sudden that just sets into motion everything that you need to do in order to form all of these rings that serve as kind of your foundation for a cholesterol molecule. And once you've done that, you've basically got this lanosterol that is really a great foundation for your cholesterol molecule. Now, lanosterol can be converted through several more steps into cholesterol. Differences between those is we've gotten rid of those guys right here, and this double bond right here, this double bond right here is now right here. Likewise, we've added double bond on our remaining chain on that cholesterol molecule, and this guy right here. You don't have to know those structures or anything, but basically what I want you to know about is getting to the point of synthesizing squalene. Once you've synthesized squalene, then you just have to do a few steps to make that epoxy ring, and once you make that epoxy ring, you're going to break it open, and then that just moves into kind of everything falls into place and cyclizes with all those rings for your lanosterol molecule. Now, cholesterol is generally going, or is in many cases, is going to be esterified with a fatty acid through oxygen, and that's going to be added by squalene epoxidase. So you might have something off of here, off of this ring on your cholesterol molecule to make it a cholesterol ester. All right, well, I hope that was helpful. I think some of the most important parts about this cholesterol biosynthesis and cholesterol metabolism is understanding your starting point and what are some of the big steps along the way to get to those isoprene units. And if you understand those isoprene units and a head to tail versus head to head, then that's going to be very helpful for understanding all of this. All right, well, thank you very much, and have a good one.